So if you've ever played around with a large language model beyond the basic hello world examples, you know there's this massive gap, right? A huge canyon between a simple script and a real production-ready agent. Well, today we're going to close that gap. We're going to put on our senior engineer hats and actually architect an AI agent that's robust, that's resilient, and that's ready for the messy real world. Let's get into it. For this whole explainer, we're going to be playing two roles. First, you've got the optimizer. This is our builder, right? The engineer who writes that beautiful, clean code for the perfect scenario, the happy path. But then we've got the debugger, and the debugger's job is to be the ultimate skeptic. They poke holes in the design, they hunt for those nasty edge cases, and they're always asking, yeah, but what happens when? Think of it like a live peer review. It's through that tension that we're going to build something that's actually solid.
Okay, here's our blueprint, our game plan for the build. We're going to start at the very bottom of the stack with a data layer. That's the agent's source of knowledge. Then we're going to move up to the model core. That's its brain. After that, we'll get into the inference loop, which is where the agent actually does stuff. We'll pull it all together for a final demo, and then we'll take a quick look at what's next.
All right, let's kick it off with part one, the data layer. You know, it's so easy to get fixated on the cool AI model itself, but we got to remember, even the smartest agent out there is built on top of a pretty traditional data stock. Getting this foundation right isn't just important, it's absolutely critical. So, optimizer hat on, here is the classic go-to playbook for giving our agent some knowledge. Retrieval Augmented Generation. You probably know it as RAG. It's straightforward. We load our documents, we chop them up into manageable chunks, we use an embedding model to turn all that text into numbers, vectors, and then we stash them in a vector database so we can search them super fast. It's clean, it's simple, and it works. Well, most of the time. And time to switch hats. The debugger looks at this perfectly clean setup and immediately hones in on the weak spot with this exact question. What if the answer to a user's question is split, right between the end of chunk 1 and the start of chunk 2? Well, our simple retriever might just grab one of those chunks, not both. And the result? The agent gets half the story and gives a garbage answer. This isn't some rare edge case. This is a massive point of failure for simple RAG pipelines. And the optimizer fires back with a much more robust architecture. See, the solution isn't to ditch RAG, it's to make it smarter. This is where the parent document retriever comes in, and it's brilliant. The logic is, we still search over those small specific chunks for speed, but, and this is the key, once we find the best matching chunk, we go and grab the entire parent document it came from. This table shows it perfectly. We give the LLM the full coherent context it needs to actually reason. Now, look at the trade-off on that bottom row. Yeah, it's a bit slower, and it uses more tokens, so it costs more. But the quality of the answer, it goes through the roof. And that is a classic engineering decision you have to make. Okay, fantastic. Our data foundation is solid. Now we can move up the stack to part 2, the model core. This is where we give our agent its brain. We're talking about the ability to remember past conversations and, super importantly, to use tools to interact with the world around it. So what even is agent memory? Well, put simply, it's the difference between a glorified search box and a real conversational partner. It's the thing that lets the agent remember what you were just talking about 5 minutes ago. Without memory, every single thing you say is a brand new interaction, like talking to someone with amnesia. That's just not how intelligence works, right? The optimizer in us loves a good toolkit, and frameworks like LangChain give us a bunch of memory types right out of the box. You've got the simple ones, like conversation buffer memory, which basically just crams the entire chat history into the next prompt. Or you can get smarter with something like conversation summary memory, where you actually use another LLM call to summarize the conversation as you go. Choosing the right one is key, you know? A quick little customer service bot might only need to remember the last 2 messages, but a long-term research assistant, it's going to need that summarization to keep track of everything. But here comes the debugger again with a huge reality check. This chart says it all. There is absolutely no free lunch when it comes to memory. Just look at these bars. If you give the agent perfect total recall, yeah, your context quality is incredible. That's that high bar in the middle. But what happens? Your token cost, the bar on the left, goes through the roof, and your speed on the right just plummets. Every single choice is a trade-off. Cost, speed, quality. A real production system has to find the right balance. Okay, let's move on to part 3, the inference loop. We've got our data, we've got our memory. This is the runtime. This is the engine room where the agent actually executes a task. And it's also where our nice, elegant design is about to meet the messy, unpredictable reality of how LLMs actually behave. The optimizer's view of the world is just beautiful, isn't it? Look at this code. We set up our agent executor, we give it the model, the tools, the prompt, we call run, and we expect a perfect answer to pop out. This is the exact code you see in every Getting Started tutorial on the planet, and it works perfectly, right up until the moment it doesn't. And cue the debugger, because in the real world, you are going to see this error a lot. See, LLMs are non-deterministic, which is just a fancy way of saying they can be a little creative, even with the same input. And when the model's output format isn't exactly what the next piece of your code expects, you get this. A big, scary output parser exception that just crashes your entire agent. The happy path just led us straight off a cliff. So how do we engineer our way out of this mess? Well, the optimizer solution isn't just one simple fix. It's about building in layers of resiliency, like armor. First, you add smart output parsers that'll automatically try again a few times if the formatting's a little off. Second, for trickier errors, you write your own custom handling logic. And third, this is the ultimate fallback, if the agent gets truly hopelessly stuck, it can use a human-in-the-loop tool. This literally pauses everything and pings a person to ask for help. This is how you build an agent that doesn't just fall over at the first sign of trouble. Okay, let's do this. The moment of truth. We have hardened our data layer, we've wired up our model core, and we've made our inference loop resilient. It is time to see our full-stack agent in action. We're going to give it a complex task that needs every single one of these components to work together seamlessly. Here is the challenge. And notice this is not a simple question. This is a complex, multi-step task. First, the agent needs to use its document search tool with our fancy parent document retriever. Then it has to analyze the results. Then it has to switch to a totally different tool to search the live web. A naive agent built on that simple happy path code, it would absolutely crash and burn trying to do this. And this is so cool. This slide is basically the agent's internal monologue. Let's look at this timeline. Step 1, it thinks, okay, first I need to look in my internal documents. Step 2, it takes that action. Step 3, it sees what it found. Then, and this is the critical part, in step 4, it thinks, okay, part 1 is done. Now I have to switch tools and search the web. Step 5, it takes that second, completely different action. Only after all of that, in the final step, does it put everything together into a single synthesized answer. That is the power of a properly architected agent. So we did it. We built a truly robust agent from the data all the way up the stack. And if there's one big takeaway from our whole optimizer versus debugger journey, it's this. Building production-grade AI isn't just about finding the hottest new model. It's about thoughtful, disciplined software engineering. It's about expecting things to fail and then building resilient, intelligent systems around these incredibly powerful, but still kind of unpredictable models. And all of this leaves us with one final big question to think about. As these core LLMs just get exponentially more and more capable, where's the real challenge for us as builders going to be? Is it going to be in architecting even more complex code and error handling loops around them? Or will the biggest bottlenecks shift back down the stack to where we started, back to the quality, the structure, and the accessibility of the data we feed these things in the first place? Something that you want. Thanks for joining me.